In this video, we're going to discuss the Doppler effect and how it changes how we perceive these line spectra. So when we've talked about emittance of light from matter, we talked about the change in the energy of the orbitals. And even for complex atoms or molecules that have many electrons around them, we still see reasonably specific line spectra. While hydrogen only has a few lines because it has one electrons, our calcium, our magnesium, our neon still has very distinct lines. Any given element only emits so many particular lines, and even if you were to try to stack all the other lines up from all the other locations, if you overlapped a great deal of all the materials in one spot, there's still gaps. There's still places that aren't filled in. If you have an object like the sun filled with lots of elements, you can imagine they're all giving off light. But nonetheless, as long as our devices are good enough, they ought to be able to continue to see gaps. There ought to be places where there just aren't any lines. So why don't we see that? Why does the sun look like a nice continuous rainbow? What's going on? Well, to put it simply, this is where the Doppler effect comes in. And there's a bit of a mix. The truth is, we do see gaps in the sun spectra. In fact, there's a little depiction over here. The dashed line shows what we should see in terms of intensity versus wavelength coming off any object whose surface who's about as hot as the sun is, where the solid line is the actual spectra we see. It doesn't quite line up. There's little bumps and divots and missing components. The truth is, we can look at the line spectra of a mix of things, like all the other stars that we can see, and as long as we have a good enough diffraction grating and spread them out far enough, we'll start to see differences and gaps and weaknesses where there's just not as much light there as there should be. Generally, this is an intensity. There is basically every wavelength, but some of them we don't have as many photons as we would expect. What's going on then? Why is it that we can see them all when clearly the line spectra don't add up to them all, but we can still notice some of the difference? The Doppler effect is most commonly described with things like sirens. So if you've got a person hanging out, standing by, and you've got a fire truck racing towards them. And it's got its horn and it's giving off sound. Well, it gives off a sound wave. But then it travels a little bit, and 1 second later, it emits another sound wave. Well, that first wave was moving forward some. And then they all continue to move forward a little bit. But those sound waves move faster than the car. The truck is definitely not moving the speed of sound. What you end up getting are these pulses of sound that are spaced so far apart. Now, if the truck was not moving, if it was holding still, so this is while moving forward. If we did this again where the truck was stationary, that horn is the same horn, it's emitting, but what we find is because it isn't chasing the sound wave, the sound waves ends up being farther apart. If the truck is moving forward, it's not letting the first wave get as far away before it emits the second wave. If the truck is stationary, then it wasn't able to chase down the front wave, and proportionately these would look a little bit different. Our front wave would be here, and we originally started with the truck further back. And so they'd look a little bit more like this. The waves will go just as far, you just won't have caught up. This is true also for when a truck is going away. If we have the truck start somewhere and go this way, well, the first sound wave gets emitted and will be here, but the second sound wave, the truck was further along. And so it travels and it doesn't get as far. And the third sound wave, the truck was further along, and so it travels and it's much farther away from the first and the second wave. What we've done is we've changed the wavelength. From peak to peak, from pulse to pulse, we've changed how far apart they are. When an object, the siren's coming towards you, it sounds higher pitched. Woo, 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 and then it passes by. Woo, 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 woo. You've heard this probably if you've ever been on the road and an emergency vehicle goes past. It doesn't have a different sound device on either side. It's just one of them, it's running forwards and catching up to its own wave, and one of them it's running past and getting further away from its own wave. The apparent frequency that you hear changes based on the speed of the object emitting it. Now, truthfully, it has a speed. The stationary truck is the actual sound speed, how fast it produces them. But what your ear hears is the difference between them. This is true for light. If an object is moving and a photon hits it, first when an object is still. So let's have a photon come in and hit an object that is still. Well, if my object is moving away and that photon comes in, it makes it look longer. It doesn't catch up quite as quick because this object is moving away slightly and that's drawing the photon out as it interacts or as it emits. This is also true for emittance. If your photon is leaving, if you're holding still, you'll have one wavelength, but if your object is moving away as it emits, it draws out that wavelength. Imagine standing somewhere and throwing a ball lightly, then imagine running away and throwing the ball. Because you're running one direction, that ball might move only a foot or two from where you let it go, despite your throw. Where if you'd been standing still and thrown it, it would have gotten a lot of distance. This is sort of the idea going on here with the photons. And if we're moving towards something, the result is that it increases it. If you ever played baseball, pick the ball, you run forward a little and you chuck it. It gives you a little bit more distance, a little bit more energy. You get to turn your speed into a little bit of the force of the throw. As that molecule changes, or that atom changes which direction it is moving relative to the release of the photon, this will change the apparent energy of the photon. As a result, despite doing the exact same change, say N2 down to N1, there's a set energy, but there's also energy of the vibration, because that's really what our atom's doing here. We have an atom, and it is bouncing back and forth. It is vibrating in all directions. In fact, all solids do this, all atoms in liquids do this, all gases are vibrating some. It's easier to see for solids. They just sit and shake. But that shaking means that they are constantly moving towards and away from all the other things, which means some of the time they're putting a little extra energy in. Some of the time they're putting a little less as it moves away, at least to the outside observer. So that same atom can emit some wavelengths of this size, it can emit some that are a little sharper, and it can emit some that are a little more stretched out, depending on what its motion was when it released it. What this means is that if we think about a line spectra, we expect a single point at some frequency. But the truth is, you're going to get some photons that are a little different in terms of their wavelength based on the vibrations. Now, if you're moving the most forward possible, you can put the most energy in, and so we'll say this one is smaller. And so there's some chance that you're putting a lot of extra in because it's moving towards you at the fastest speed. We'll call this one larger wavelength, and there's a chance that you are at the maximum away speed. But the reality is that's a very narrow motion. If you're moving back and forth, most of the time you're not at the most speed one direction or another, you're somewhere in the middle. And so what we actually get is a spread. Because of the possible speeds of going forward and backward at any moment when that photon is released, we get a spread. And if you have a really good device at very low temperature, you can actually see all these individual peaks. Because vibrations are also quantum, because you can only vibrate at certain speeds. And we talked about asymmetric, symmetric, bending and rocking, those type of vibrations. There's only specific energies of vibrations. We get very specific peaks. Most of the time our device isn't this good, and what we get is a curve. It can't quite differentiate them. But really good devices and very cold temps can actually see the individual vibration speeds that are adjusting the photon's energy. Well, this means if you have a line spectra with a bunch of lines, the truth is they spread out. Which means what you really get is a hybrid of all of them that looks like the overlap. Well, the higher you can heat your material, the more vibration mode you can reach, the more spread out they get. And the sun is a very hot object. This is where black body radiation comes from. If you have a ball of iron, you just start heating it up. It starts glowing a little red, it starts glowing a little yellow-orange, it starts glowing white. You're just heating it, increasing the vibrations, and those vibrations are spreading out over each other, filling in all the space. This is what the dotted line at the start was. This is what we expect, based purely on spreading out vibrations, the sun should look like. But the sun kicks out lots of dust, or high energy particles, but they start to cool as they get a little ways away from it. There's a little bit of hazy, random particles, for a few million kilometers outside the sun. They absorb light. They've cooled off a little bit, and so as the light from the sun hits them, they can absorb it. And so we see these missing little peaks. We see, hey, there's not as much energy of this wavelength as we expect, and there's definitely some of that one missing, and there's definitely some of that missing. By being able to look at what's missing, we can determine what must have been in the upper atmosphere of the sun absorbing those wavelengths. This is how we can actually tell what stars are made out of. How much of different metals are in that star. We can look at where these slight absences are in its spectra. The Doppler effect explains why we can see more colors than we should see from the line spectra alone. But additionally, they help us understand why we absorb more color. Your atoms are vibrating all the time. So whether they're emitting or absorbing, they can absorb a range of energies around their transition. So if we're trying to absorb, and it's supposed to be, let's say, 675 nanometers. Well, the transition between one orbital and the next is exact. There's a set amount of energy. And so we should only be able to absorb exactly that amount of energy. But your atoms are vibrating back and forth, and so sometimes you can absorb just a little bit more or just a little bit less in the same way. It's basically the reverse. And so there's an absorption curve. There's a block. The hotter you are, the more spread out this is. The colder you are, the sharper it is. So a cold spectra will have a very sharp one. A warm spectra will have a broad one, and a hot spectra would have a very broad one. The more you are vibrating, the more you can absorb off of the ideal energy. And so a lot of experiments are done at cold temperatures. It gives us better graphs. It lets us see more clearly and notice little peaks and differences. A hot graph often can hide small absorptions Well, a cold graph lets us see them very, very accurately. There could actually be another absorbance right here that we normally just can't see. Another transition, say one of these peaks might be a 2 to 1, or one of these might be a 3 to 7, or something like that. They could have similar energies, but one's just way less likely to happen, and so we don't see as intense a peak. But at room temp, you didn't see it at all. They were so spread out, it was hidden under the broad graph. And so an advantage of doing things at cold temperatures is that we get better readings. And in fact, we have to do this for a lot of equipment. If you ever wonder why MRIs are a bit expensive, yeah, big magnets and things, but the big part is keeping them cold. We need superconducting magnets, which means we need liquid helium, down around 4 Kelvin. So keeping sensitive equipment cold enough to get good data is very difficult. That's actually why a lot of our space telescopes eventually die. We need them quite cold to take these measurements, and they only have so much liquid helium on them. We send them up, they eventually run out, and the instruments can't see anything. They just get broad peaks at that point because they are too hot for the detector to actually notice the difference in absorptions. The detector itself starts warming up and vibrating, and so it changes the energies that it sees absorbed. This is the idea of the Doppler effect. It's all about the vibrations of the atoms.